All right. Well, good morning and good afternoon, everyone, and welcome to today's Exploring by the Seat of Your Pants event. My name is Joe Gorowski, and I'll be your host for today. If you've been tuning in this month, you know that we are celebrating World Space Week. So we've been connecting with scientists, with engineers, with astronauts, and they've been sharing their amazing experiences exploring our planet, both on the ground and obviously above, but also all of the behind-the-scenes work that it takes to build the machinery, the equipment, the rovers, the launch crafts that make it possible for us to explore beyond the Earth. So it's been an absolute blast. If you head over to exploringbytheseat.com, you can find all the events that are still coming up. You can register to tune in live or join in via camera spots like many of our groups joining us today. Today's event is a great one. Today we are joining Julie Newman. Julie is an electronics engineer at NASA's Jet Propulsion Laboratory. In 2019, she won the prestigious JPL Charles Elachi Award for exceptional and critical contributions to the development of the radar instrument for the Europa Clipper Mission. So this hardware that she's helping to build is going to be used to measure and map the icy surface of Jupiter's moon Europa and help the search for alien life. Previous to this, she studied electrical engineering at the California Institute of Technology, or Caltech. So I'm going to bring Julie in live with us today. Julie, how you doing?
Hi, everyone. Hi, Joe.
All right. Well, it's so great to have you joining us live from the West Coast. We're excited to get to know you a little bit better today. I'm going to let you take over for a bit, and then we've got a great group of classrooms who are going to fire some questions at you.
Great. Okay, let me get this screen share going. This one, and there we go. Okay, is that up?
We're good to go.
Great. All right. Hi, everyone. Thanks, Joe, for that introduction. I'm Julie, and I'm here to tell you some very important information that I wish I would have known when I was your age. And it boils down to this: engineering is awesome. And I'm going to tell you why I think you should consider pursuing it as a career. So let's get things started. First off, I want to show you two really cool photos. So this is a picture of me in 2006 when I was 13 years old on a vacation with my family. It's my dad and my two older brothers. And when I was your age, I was interested in a lot of different things. And one of those interesting things was space. And on the day of this photo, we were actually getting a tour of a really cool place that has made a huge impact on expanding our knowledge of outer space and the solar system. And I want you to take a look at that spot right above my shoulder on the right, because this next photo was actually taken at that exact same spot 13 years later. So these are both at the NASA Jet Propulsion Laboratory located in Pasadena, California, which is near Los Angeles. And this is the award that Joe was mentioning. So I love bringing up these photos. This photo on the right was last year, getting the award for my work on the radar instrument that will explore Jupiter's moon Europa. And when I was on that tour in 2006, I remember thinking that it would be super cool to work at JPL someday. But honestly, I had no idea that I really would. When I was 13 years old in that photo on the left, I didn't know what I wanted to do yet. And I imagine that a lot of you are in the same situation right now. All I knew was that I liked my science classes in school and I loved science competitions. And honestly, I figured I'd become a scientist one day, but it turned out that I was lucky enough to find something that was actually a much better fit for me, and that was engineering. And so I'm guessing that you, like me when I was younger, don't know a whole lot about engineering. You have a science class at school, but you often don't have an engineering class yet. And if I had known then as much as I know now about what being an engineer was like, I would have been super duper excited. And it would have given me a much better picture of what would happen between that photo on the left and the photo on the right. Okay, so thinking about your future, next natural question is this, right? What do you want to be when you grow up? You've heard it a million times, and it's a terrible question, and I think it's the wrong question. And I think a much better question is this: what types of problems do you want to help solve for other people? So all jobs are about helping other people and solving other people's problems. For example, a mechanic will fix your car problems, and the chef at a restaurant helps solve your hunger problems. Ultimately, everyone in society is doing something that helps other people in some way. So when you think about what you want to be when you grow up, I want you to think about what kind of problems you want to help solve for other people. And guess what? If you want to solve cool problems, I have some great news for you. Engineers get to solve cool problems. Nearly every man-made object you've ever touched was directly designed by an engineer. Honestly, the entire modern world day economy is built on a foundation of tools and machines and factories and transportation and devices and innovations, all of which were designed by engineers. So I know what you're thinking. What do engineers actually do? When I say that engineers design and build things, what does that really mean in terms of actions you would do day to day as an engineer? Well, the best way for me to answer this is to show you. I'm going to walk you through an in-depth real-life example, and that example is me. I'm going to show you in as much detail as I can the types of things I do as an electronics engineer. And even if I were a different type of engineer, a lot of aspects of my job would be very similar. It would be, the difference would be that I would be using different tools from a different sub-branch of engineering. I love my job. I've been at JPL for almost 6 years now, and it's been awesome so far. The problem I'm currently working on is this. Can we make a radar to study Europa? So remember, all jobs are about solving problems for other people. What JPL is doing is solving a problem for NASA. NASA has science objectives, and they want to collect new and interesting information about Jupiter's moon Europa. JPL is in charge of building a spacecraft for NASA, and this involves solving a lot of separate sub-problems. The part of the problem that JPL has assigned to me is to help design and build a radar instrument for measuring the ice at Europa. So radars work by sending out radio waves towards something and then receiving the echoes that bounce back from it, kind of like a bat that uses echolocation, if you've heard of that. By interpreting the echoes, you can learn a lot of different things. And in our case, it will help us determine the topography of Europa, the surface, how thick the ice shell is over its subsurface ocean, and where the thin spots in that ice are. If there are large bubbles of ocean water close to the surface, like you can see on the picture on the right, some scientists suspect that those are there, and if they are, my radar will be able to detect them. And we're particularly interested in those near-surface lakes because some scientists believe that that water at Europa could actually harbor alien life. So I think it's pretty clear to say that I get to work on some really cool problems. Now, let me tell you what I actually do. As I work through each step in taking this idea from a radar instrument and turning it into a real thing, I encounter new problems and have to find answers to new questions. So the first step in any engineering project is research. It's how are we going to do this? No one has ever done this before. I get to ask that question a lot while working at NASA. So the first step is doing research. Unlike a test at school, in real life engineering, you're allowed to use any resources or of information you can find, which can include textbooks, results from previous studies, data from previous space missions, journal articles, the internet, and even asking advice from other engineers. Even though this exact radar instrument has never been built before, we can learn a lot from previous designs and previous similar experience. A lot of very good technical information already exists about how to build electronics that go into space, and we make the most of that information every time we're making something new. Step 2. So big problems like this are split up across many different engineers. Everything is very collaborative. We have to figure out what all of the different parts of the system will be and who will design each part. So we'll often put together block diagrams like this one as we're deciding what the different parts should be and how they should connect. I'm designing the green box in this thing, which is the radar control electronics, which you can think of sort of like the brains of the radar. Other engineers on the team are designing all the neighboring parts, and we all have to work together. So step 3, what are the requirements? Building a radar for a spacecraft is complex, and there are a lot of different requirements. So these are things like how big it can be, how much it can weigh, how much power it can use. And I also need to talk with the other engineers designing the spacecraft to figure out how the specifics of the environment that about the specifics of the environment that my hardware will experience. What are the minimum and maximum temperatures? My hardware is going up to space. It's not me going up to space. But just like I would want air conditioning if I were going, my hardware actually can only survive in certain temperatures. And then similarly, how much vibration will my hardware have to survive in the rocket launch? Rockets are not exactly a gentle ride to space. How bad is the radiation at Jupiter? And how are my electronics going to deal with that? Which, hint, it's really, really bad at Jupiter. There's really high radiation. And what does all this mean for how I should approach the detailed design of my radar electronics? So step 4, what electronics can I use and how should I connect them? So with all those requirements in mind, the next thing I do is start picking out the actual parts, the chips, the resistors, capacitors, etc., to begin what's called the schematic design of the electronics of my radar. So that's the parts are those little bugs up on the top right. If you've ever opened up electronics and you see lots of little bits sprinkled around, that's these guys. And in particular, for me, with this design, I have to consider the radiation requirements when I'm selecting these things. Most types of electronics actually won't work in space, in part because of radiation effects. If you took your cell phone up to space with you, it definitely wouldn't work for very long. And I have to design my mission to survive being in space for many, many years. So when I've got a good idea of the parts I want to use, I begin working on the schematic, which is this fancy diagram in the bottom that's basically just a pictorial version showing what should connect to what, and to form circuits. And so this is a lot of what you learn in school, is how to make these circuits. And I also use specialized software to simulate portions of the schematic to see if my idea for how the circuit will work are on the right track. So like in this upper right, I can actually make it produce the waveform that I'm trying to make. So I didn't design the chips themselves, the little bug-sized pieces. Those were designed by a different type of electronics engineer at the company that we buy them from. That engineer already solved my problem for a portion of the circuit already, and I can use that chip instead of having to make my own special complicated circuit to do the job of that chip. And that other engineer saved me from having to pick out individual transistors to use in the circuit, which makes my job much easier. And I bring this up because engineering is very collaborative in this way. There are even special engineers at JPL whose main job is to review designs of engineers like me just to guarantee that they'll work in all situations. And they do special types of analysis that check how the circuit's operation will change across the different temperatures and across different radiation, etc. So you might have noticed that I've used the word design a lot when describing what I do. And I think most people only think of that word as it relates to art. You think about the design of a painting or the design of a house. But it applies perfectly to engineering because a lot of what I do involves constant creativity. I have to brainstorm all of these ideas and then figure out which ones will work and which ones will work best for my application. Sometimes I have to get really creative with the solutions to use parts in ways that they weren't necessarily intended to, but that will work for me. Okay, next. The next step is taking that schematic, which showed how the parts should be connected, and then generating what's called a printed circuit board layout. This is the start of taking the idea of a radar and the initial concept design and translating it into something that will become a real physical object. This task is quite literally like doing a jigsaw puzzle. I have to decide where each part in my circuit will physically sit and how to get them all to fit in the allotted size and how to draw all the wires to connect the different pins of each part. Printed circuit boards, which are the flat parts of electronics, if you've ever opened anything up and seen it, are actually layers of different alternating metal and not metal to make sort of this nest of wires. And I have to figure out exactly how many layers I need to actually build the network of highways and overlapping freeway interchanges in a way that my design will require. So in this example picture from another design, Everything shown in red will be on the top, and everything shown in blue will be on the bottom. And you can continue this for internal layers. So my radar board is actually much more complicated than this, and it'd be hard to look at on a single slide, which is why I have this simple version. My board has around 2,000 different parts and requires actually 20 layers of different signals in order to actually undo that rat's nest and connect the things to each other that need to be connected. So it's a really fun challenge, and if you like doing puzzles, you love doing this. And the software also actually can make generate a 3D model like the picture you see on the right, which is helpful in the next step. Step 6, what type of box do I need? So boxes for electronics that go into space are actually pretty complex. Luckily, JPL has a lot of mechanical engineers to help me with my needing a box problem. The box needs to be strong enough to keep my electronics safe without being too heavy. The box has to be designed to act like a heat sink because all electronics dissipate heat, and you need to get that out. The box has to act as a shield for my electronics and protect other neighboring electronics from radiated interference that my board will produce. And if all that wasn't enough, my box also has to protect my electronics from incoming radiation, like I talked about when I was selecting chips to use on the board. So the design and validation of boxes like what I need for my hardware requires the help of engineers that specialize in each of these areas. Did I skip? Okay, step 7, and this is a picture of me with the actual hardware I'm telling you about. So next is that we actually build this thing, and businesses help other businesses solve problems. So to make a printed circuit board, it takes an entire factory of dozens of specialized machines, like you can see in the picture on the bottom left, which, by the way, were also designed by other engineers, and a lot of specialized knowledge. So it's common for most companies like JPL that design new electronics to utilize outside vendors to do the manufacturing of the design. So as an engineer, I'm actually not always solving purely technical problems. In this case, my problem is to figure out which companies have the capabilities necessary for building my electronics, my design. Then I have to communicate with those companies and talk with real people and get them to commit to a price, and then handle all of the paperwork for the contract, for the build, and get JPL management to approve and sign off. And it's not uncommon, honestly, for coordination problems with this stuff to feel more challenging than technical problems sometimes. Okay, step 8. Does it work like it's supposed to? So after we get the board made, we put it through a lot of rigorous testing to make sure it works how it's supposed to. And we also do tests with it connected to the other parts of the system to make sure that the radar will work all together like it's supposed to. So during the earlier design phases, I spent a lot of time pre-COVID in meetings, in meeting rooms and conference rooms with other engineers, and in my office working on the computer. Since then, it's been my home office. And once the hardware arrives, though, I spend most of my time in the lab, actually testing with it and actually holding it. This is my favorite part of the project, and when I actually get to touch and play with the hardware itself, which luckily will be starting back up very soon for me. When we do a lot of testing and almost always some fixing of the electronics. It doesn't work perfectly the first time. And once we think we have it completely working, we mount it in our special custom boxes and put it through even more harsh testing. So this picture on the right is when the electronics are in their box, and it's actually sitting in what's called a thermal chamber, which is kind of like a fancy oven that will actually cook my box to make sure it can work hot, and will freeze my box to make sure that it can work cold. So in real engineering, you get to learn a lot each time you make something, and it's often impossible to get every aspect of the design and build perfect on the first go. So there are there are just too many complex things to solve all at the same time, and when you see it, you think you can do it better the second time. So at JPL and most aerospace companies, we usually go through this design phase 3 times. So that means we're going up to the beginning steps and doing them all over again so that we can get it right for the final one that will actually go into space. So after we've done all of these iterations and have our final working product ready, what's the end result of all this? That's delivering the fancy hardware, of course. The completed radar unit gets delivered to other teams at JPL for integration with the rest of the spacecraft. And in the not too distant future, the final spacecraft will be completed and launched on a rocket towards Jupiter and Europa. And I have these cool pictures. Fun fact, the radar instrument, which is inside of that big case that I'm carrying, the radar instrument is so special and expensive that JPL considers it too risky to send in the mail. So when we're done building and testing the unit at the company where we had it manufactured, I have to personally bring it home to JPL, and I pack it up in this fancy box and bring it on the airplane with me. And we even buy the box its own seat. And yes, it is wearing its own seatbelt in that picture on the right. And interestingly enough, the box just so happened to be too big for the economy class seats. And so I had to sit next to it. The box had to ride in first class, and I had to sit next to it to supervise, luckily. So it was really fun seeing the looks of all the passengers on all the passengers' faces when they saw this, when they were boarding. It's not every day that you see something labeled NASA and fragile mission critical space hardware inside. And I had a fun time talking with the flight attendants, and even one of the pilots came back to ask me about it, and I told them all about it, just like I'm telling you. So I've told you about my one example as an electronics engineer, but there are tons of different types of engineers, and I'm positive you could find a type that you would really love. So if you really like robots, try looking into what it would be like to be a mechanical engineer. Maybe you're interested in helping people with health problems, but you don't want to be a doctor. Then take a look at biomedical engineering. Maybe you just want to build things that people think are fun, like roller coasters. Well, then civil engineering might be for you. Want to help the environment by manufacturing new kinds of pesticides that won't negatively impact the water supply? Go be a chemical engineer. And honestly, I could go on like this for hours. Engineering is really broad, and there are an infinite number of different ways of applying it to solve different problems for other people. If you want to help people make the world a better place, engineering is a great choice for you. And I think it's really important to point out for all of you students that engineering is actually very different from being a student, and I think it's way more fun. So engineers don't have to memorize anything. In fact, it's encouraged for you to go look up the answer you need from a textbook to double check yourself. And in school, there's only one right answer to each problem, but in real engineering, there isn't one right answer, but a lot of right answers. You know, there's no one right way to build a car. There's a lot of different types of cars that solve the problem of transportation in different ways. So Ferrari decides to solve the problem for speed and aesthetics, but Ford is deciding to solve the problem for economical solutions with good gas mileage. So creativity is super important. In school, you sometimes have to solve a problem on a test in under an hour and without using the internet. But in real engineering, you generally have days or weeks or even months to solve a problem. And you're allowed to talk to other people, read books, try out some examples, run some tests to collect new data, anything to figure out a good solution. And collaboration is a huge part in that solution. So foundational skills you learn in engineering school actually make it so you can learn almost anything, even out in normal life too. And if having fun working on cool problems, helping people, and making the world a better place weren't already enough reason to want to become an engineer, there's a few more perks that I think you should really know about. So being an engineer, not only really cool and interesting, but it also pays really well. As an engineer, you're able to solve problems for companies, and solving problems produce a lot of value. If a company wants to release the next iPhone, or it wants to make the next biodegradable plastic, or produce the next medical technology, they need teams of engineers. The world is happy to make use of as many engineers as there are available. There's pretty much a bottomless demand for good engineers. Even NASA, a place that people incorrectly think is full of only scientists, actually hires 10 times as many engineers each year as scientists. So if you want to work for NASA, better place your bets on it would be smarter to place your bets on engineering than it would be on science, actually. So when you actually look at the data and you rank college major choice by salary, 9 out of the top 10 are all engineering. In fact, the average engineer, at least in the US, makes almost twice as much as the average college graduate. Unlike a lot of other disciplines, engineering doesn't really require that you have advanced degrees to get your dream job. I, for example, only spent 4 years in college, and I have friends who graduated from undergrad at the same time as me, but are still finishing their PhDs right now. So the world needs more engineers like you, and the world needs especially more engineers that love what they do. Being an engineer is really interesting and very fulfilling. You get to work on solving some of the coolest problems out there, and you get rewarded by society for doing so. I hope you'll try it out and see if it's a good match for you. If it is, I think your future self will really thank you. And I hope that I've given you some more insight into engineering than you had before today. So thanks for listening, and happy to answer all of your questions.
All right, very cool. Well, Julie, thanks so much for that great presentation and taking us, backstage on what it takes to be an engineer. I'm gonna say though, I'm a little disappointed in that the picture that you shared. I thought the briefcase would have been handcuffed to your wrist. So.
Oh yeah, we did suggest that. It's fun actually. I walked through TSA with a packet of paperwork that tells them they're not allowed to scan it and that they just have to trust me. What's in the box is what I say is in the box. And they actually take the box from me because we don't want it x-rayed, because of course that would impact the electronics. I hand them the paperwork, they check my passport and stuff, and then they take the box, and I still have to go through the metal detector and things, but they just take the box right around and hand it back to me on the other side. No questions asked. It's really, it's a very unique experience for sure.
All right, very, very cool. Well, let's start meeting some of our groups. Let's take a few questions before we wrap up today. So we've got Gabriel joining us. He is in Waterloo, Ontario, so in Canada. Let me bring him in. There we go. Hey, Gabriel.
How long did it take to make the radar?
So I've been working on this project now for about 3 years, and we're coming very close to the end. So I think from the first inkling of design of the idea of wanting to build a radar, some engineers have been trying to propose it, and I think the first idea was maybe like 10 years ago, that Europa looked interesting and we'd want to go there, and building a radar for Europa would have to be special and unique. And so we started the actual real detailed design about 3 years ago, and it's almost done. It should be done in a few months.
And you did it 3 times.
All right, let's bring another group in here. We've got Ms. Alanote's group joining us in Kitchener-Waterloo. How are we doing today?
Good. Your hardware will be used to help search for alien life. Have you discovered anything so far that you can share about aliens, or how your hardware will be able to help detect alien life?
Yeah, so I can tell you we don't have any aliens. We're not hiding them. I don't have any coworkers who are green. But so what my hardware will do is actually hopefully prove some ideas and hypotheses about what we think Europa is like. And it will find those bubbles of water near the surface that I was talking about. And from the models of what we think Europa is like, the water in that area would actually be very similar to Arctic water. And it would potentially, even if you took a fish from the Arctic and just plopped it in there, it might be okay with it. So we are flying with a suite of different instruments, some cameras and some mass spectrometers. And so we will be able to, if there's a space whale and it's big enough for me to see on the radar, I will definitely let you know. But otherwise, it's going to be a bigger process. I'm probably not going to see the life directly with my radar, but I could be confirming that a spot that could harbor life is in fact there. And if this mission goes well and Europa still looks interesting by the time we get there, we're actually planning to do a follow-up mission, which would be a lander that would drill through the ice at the thin spots that my radar had found, so that we could get down to that water and actually directly sample it to look for that life.
All right, very, very cool. We've got Mrs. Rodriguez joining us. She's representing her grade 7s in Los Angeles. How are we doing today?
Oh, great. Thank you.
All right. Well, if you have a question, we'd love to grab one.
Yes. My student Angie was asking, how long does it take to build a robot?
How long does it take to build a robot? Well, it depends on your requirements. People usually think of robots as things with wheels, and you know, JPL is also known for doing the Mars rovers. I think there's some people working on Mars that are tuning in for next week's sessions. So it depends on your requirements. You know, you can build a robot at home in days. If you want to send it to Mars, it's usually going to take you a few years, because you want to make sure that when it gets to Mars, that it's going to work right, and that it's not going to get stuck on a rock or accidentally flip over. The missions for NASA will take understandably longer. But yeah, if you want to build a robot at home, by all means, like, go on Amazon Prime, order a little robotics kit, and you can get yourself up and running, for sure.
So Julie, I think, you know, when people also think of robot, I think they maybe think of like Lost in Space or something, like humanoid looking kind of thing. But what is kind of the official definition of a robot?
So a robot is really, you know, it's more of an autonomous system sometimes, or it can be a controlled system, but something that's able to interact with the environment without people being there. So at JPL, actually, we are exploring the solar system with robots. So my space probe, which is, you know, like an Earth satellite, which you can see in telescopes and things, is technically a robot. You know, it doesn't have hands, but it does have eyes, and it does have like I was saying, you know, the radar sort of acts like echolocation for bats. So when bats make that little screechy sound and then they can hear the echoes, it's a lot like that. And so we are really, you know, at JPL, our thing is robotics, exploration of the solar system with robots. So we don't send any humans at JPL. That's other NASA centers. We send robots, and we think the robots can go much farther and visit much cooler places than we're able to yet with humans. So the definition of robot has only gotten more complicated as technology has progressed. I think if you took, you know, if you took a lot of things from today and took it back 100 years, they'd want to call it a robot.
All right, very cool. So we're heading to Wisconsin. We've got Joe and Zeke hanging out with us today. How are we doing?
Good. How long have you been an engineer for NASA?
I have been an engineer with NASA for 6 years. But honestly, you can become an engineer much sooner than that. I think a lot of stuff I did when I was younger, even though I didn't really know the word engineering yet, actually were engineering things. So back in middle school and high school, I did a science competition called Science Olympiad. And for that, I built a lot of little devices. So like small robots that had a task to try and pick up a bunch of different objects as fast as possible. And also like model airplanes and even little rockets and things. And even though it was called the Science Olympiad, all the stuff I was doing in that was engineering. I just didn't know the word yet because, of course, I had science class at school. I didn't have engineering class at school. So you can be an engineer now and start learning it. And then, yeah, one day come join me at NASA. I'll probably still be there.
All right, very cool. I'm going to bring another group in here. We've got Ms. Ortega representing her group, grade 7s in San Fernandino. How are we doing, Ms. Ortega? Oh,
You're
can you
on-
unmute for me? I think when you came back in, it muted on us.
The same school as Mr. Ortega, San Fernando. We were wondering how long it would take to get it to Europa,
how to make it there. Yeah.
make it there.
So actually, at the same time that I'm developing, the radar and the mission, they're actually working on building the rocket that it will go on. So NASA is working on a new rocket that will be bigger and be able to get us there faster. And with that rocket, it will take 2.5 years just in cruise to get to Europa. And we really want to use that rocket because if we use a rocket that exists today, it will take us more like 6 years to get there. Jupiter's really far away. So it's gonna be very interesting to wait. I hope we get the fast ticket and not the economy ticket.
So a question that I was thinking about while you were describing the radar that you're building is, what is that sweet spot, that thickness that you're looking for that will say, yeah, this could be a good spot to try to send a second mission?
The sweet spot of where we would see water, honestly, if we see water anywhere between just below the surface and 10 kilometers below the surface, we probably still want to go. The thicker the ice is, the harder that second mission is going to have with melting that ice and getting down into the water. But it's a really interesting sort of theoretical ecosystem, these water, these like subterranean lakes. It's almost like a cave filled with water, and it gets this perfect mix where it's exchanging chemicals with the surface. So Europa, it sort of looks like tectonic plates of ice almost. So they're subducting and sort of cycling with the ocean. And that means you're getting a lot of chemistry from the surface into the water, which is like mixing it up. It's almost like you're getting, like fertilizer and nutrients down into the water. And then the water that will be up in the ice will sort of be insulated and could be sort of warmed by outside radiation and by thermal heating of the moon. And so it sort of becomes like this cool little biosphere that could easily trivially have like space bacteria, but could also theoretically have like space fish or space whales if we're going that far.
Very cool. But so, one thing that we talk about is extremophiles. So bacteria that can live in crazy conditions. So on Earth in heat, or maybe high salinity, or, depth and cold temperatures. So I'm thinking that's probably a lot too of what maybe the scientists are thinking about, is that kind of life, how to find that kind of life that can live in those environments. Yeah.
So I would be even less surprised to find extremophiles. We think that Europa also has like geothermal vents at the bottom of the ocean, but those of course are much harder to get to and to go see. So we want to find life closer to somewhere we could actually detect it and then eventually go visit it. So that's why this higher level biosphere is more interesting. But I think certainly from the planetary perspective, if there's geothermal vents and we think there are extremophiles there, well, I think evolution would mean that eventually those bacteria and those little crabs and things would want to go higher in the ocean and go to more nutrient-rich areas from a different mechanism and with competition. So I would think that an area you would find extremophiles, that you could also find more less hardy life too.
All right, very cool. So you can squeeze in at least maybe one or two more questions. So give me a wave if I need to visit your group again, and we'll grab another question from your group. Oh, am I seeing a wave? I think I'm seeing a wave. Let's go back to Wisconsin.
What's the coolest robot you've built?
Coolest robot I built is definitely this current one. I also worked on a robot that will be an Earth satellite. So it will orbit the Earth and it will be looking at, it's a radar that will be looking at the ocean. So It will be looking very precisely at ocean height and down at the level where you can see, where you can even see like ocean currents and things. And that was a pretty cool robot. It should be launching, I think, like next year. And I actually, for that one, it was a collaboration with the French Space Agency. So I got the opportunity for some hardware testing to actually fly to France to work with them, which was really cool. Another interesting perk of my job. You don't usually think that you'd get much travel in, but I have. So,
and I think that's really cool about, space and space exploration is sometimes countries that maybe don't get along politically can somehow, still work together, like Russia and the US and China and India, for these kind of bigger missions, these kind of missions of humanity. That's pretty cool.
Yeah, and I will say without a doubt, the talking engineer to engineer between the French ones and US space agencies, we're best buds, like from the first moment. Like we want all the same things and everything, and it was a good old time. Still had to. My French is not very good. It's terrible. In fact, I don't know any. But yeah, it was fun.
All right. So one more question here came in from our classes in Los Angeles, and they're wondering if you were excited by that recent article about Venus and the potential.
Yeah, absolutely. I think Venus. So for some background for the other people on the call who haven't heard, Venus. A recent study came out saying that they detected something in the atmosphere that could be indicative of life there. And the interesting thing about Venus is it's a runaway greenhouse effect. So the actual surface of Venus is really hot, and really, we don't think anything could really survive there. Maybe some crazy extremophiles. But the more interesting thing is actually it has a really thick atmosphere. And so if you're in the upper atmosphere and above the clouds, it's almost kind of like you're in an ocean. It's thick enough, there's enough convection and things, but you could legitimately have like floating bacteria and things just in the air. And that's what they're hypothesizing that study could be detecting. I think Venus is really cool. I've actually thought that Venus could have life for quite a while. I think it's another high up on the priority. And in fact, even I have a colleague at JPL who's working on a Venus radar mission, which would be looking at the atmosphere more and looking back at the surface and trying to get better. It would be for making a better model of what we think Venus is. So that could be really cool. I might even go work on that mission next, actually, because it sounds really cool.
All right, very cool. Well, first of all, I want to give a big shout out to the groups who joined us today. Thank you for the great questions and spending some time with us. And Julie, thank you so much for really putting a spotlight on the career of engineering. And today's been an exciting day because it worked out that we really focused on women in STEM today. We hosted astronaut Nicole Stott earlier today, and then this afternoon we have Abigail Freeman, who works on the Curiosity rover. So it's really great to be showcasing women in STEM in all kinds of different positions. Did you have a role model or somebody kind of who you looked up to as you were growing up?
I think it was more of just a combination of a bunch of different people. And I had supportive teachers. I had my AP chemistry teacher in high school was really lovely, and she also acted as the volunteer who ran our Science Olympiad competition team. And so, I think she had a big part. So listen to your teachers. They're great. And they can help tell you about more things that you'll be interested in and get you to events like this where you can talk with people who actually went that direction. So.
All right. Very cool. Well, Julie, again, thank you so much for joining us and sharing your story today. I hope everything goes well as the Europa Clipper gets closer and closer to launch, and maybe we can connect again closer to mission time. That would be really cool.
Absolutely. Thanks very much. This was super fun. And for the Los Angeles classrooms, write down my email, and when we're out of COVID and things, maybe I can come see you in person.
All right. Very cool. Well, I can definitely pass that their way if they're interested. So thank you so much, everybody, for joining today. Julie, thank you so much. And we're going to sign off for now.
Thanks. Bye, everyone.